Finding the coordinates of a vector is easy, right? For this vector v, it's obvious. We go 3 units in the I direction and 2 units in the j direction. The coordinates are 3, 2. Simple. But what if our world is skewed? What if our building blocks aren't at a perfect 90-degree angle? What are the coordinates of vector v now? How much of b1 and how much of b2 do we need to build v? Suddenly, our simple problem is a lot harder. To solve this, we need the most useful tool in linear algebra, the orthogonal projection. Welcome to Decoding Complexities. I'm Pradeep. Let's simplify the mystery. We just need to figure out how much of our vector v points in the direction of this one axis b. Geometrically, we are looking for the point on the line of b that is closest to the tip of v. This closest point defines our shadow vector, which we will call the projection p. And the fact that it's the closest point gives us one crucial value. The line connecting the projection p to the original vector v must be orthogonal to the direction p. Let's call this connecting line the error vector e. So e equals v minus p. And what did we prove in our last video? If two vectors are orthogonal, their dot product is 0. This is the key that unlocks the entire mystery. Now we can solve the case. We have our clue b dot e equals 0 and our definition of the error e equals v minus p. Let's substitute that in. We also know that our mystery projection p is just a scaled version of b. It's p equals c times b, where c is the unknown coordinate we are looking for. Let's substitute that too. Using the distributive property of the dot product, we can expand this. And now we can isolate the one thing we have been hunting for all along, the scalar coordinate c. And there it is. The coordinate is just a ratio of two dot products. It's the dot product of the original vector with the axis scaled by the squared length of the axis itself. To get the final projection vector p, we just multiply the scalar c by the direction b. This formula is our universal tool. But remember the gold standard from our last video, the orthonormal basis. What happens if our direction vector b is a unit vector? If b is a unit vector, its length is 1. The dot product of a vector with itself is the square of its length. So b dot b is just 1. If our basis is orthonormal, the entire denominator disappears. This is a massive engineering win. By using an orthonormal basis, a complex calculation becomes trivial. For a computer doing billions of these calculations, this simplification represents a huge gain in terms of speed and stability. This is why we care so much about orthonormal basis. In Python, we can implement this directly with NumPy. We define two vectors v and b and calculate the scaling factor c by dividing the dot product of b and v with the dot product of b with itself. And then calculate the projection vector p by scaling the vector b with the scaling factor. This gives us the projection of vector v. So, by starting with a frustrating problem, measuring coordinates in a skewed world, we discovered the need for a new tool. The orthogonal projection is that tool. It's our universal method for deconstructing a vector into its components. We have learned what a projection is, and we have proven why it becomes so efficient when our basis is orthonormal. But that leaves us with a huge question: how can we use this powerful projection tool over and over to turn any messy skewed basis into a perfect orthonormal one. If this deep dive was valuable, hit that like button and be sure to subscribe, because in our next video, we will decode the beautiful algorithm that does exactly that, the Gram-Schmidt process. Thank you for watching, and I will see you in the next one.